عالی. Okay. We have Dr. Ahmadi here.
اسلایدهای من واضح پخش میشه؟
بله آقای دکتر. بله هم صداتون هم اسلایداتون پخش میشه. اجازه بدید من شما رو معرفی کنم و شما شروع کنید. So now we have Dr. Ahmadi. I said you about him that he is expert in outbreak investigation, designing a study. He is a medical doctor. He's passing his PhD nowadays, and we will be with him till now, till noon today, regarding the study design. And Dr. Ahmadi, please start.
In the name of God, hello everyone. Today I want to talk about study design and outbreak investigation. My name is Yasin Ahmadi, a medical doctor and a PhD student of epidemiology from Iran University of Medical Sciences. You can write my email as you see on the screen, and you can contact me if you have any question or any work with me. So first, I want to introduce the resources and references regarding this presentation. The first one is Field Epidemiology book, a Field Epidemiology book. Third edition from Oxford publication. I used the chapter 8, designing studies in the field. I used the chapter 8, and I teach you in this session the 8th chapter of this book. Another resource is the CDC Field Epidemiology Manual, which is about designing and conducting analytic studies in the field. And the other source, which is a well-known book, Gordis Epidemiology, a textbook of basic epidemiology, and in some slides I used this resource. So first of all, I want to talk about definition of epidemic. We have endemic and epidemic. Epidemic is a time when the observed cases of disease is further than the expected number of the disease. For example, as you see in the figure, at the first times, we have endemic, which is limited to some places, and the observed cases are like the expected cases, and then the observed cases exceeds the expected cases, and we have epidemic. So this is the definition of epidemic. Now I want to talk about the steps of outbreak investigation. I used the Gordis source for this part. Let me do you see the full screen and the title of the table here? because I see the setting of meeting software on the title of the table.
Is the title of table Steps in Investigation and Acute Outbreak?
Yes, yes.
So we all set and we are able
O-
to see the topics. So go on.
Okay, okay. I could not see, but you can see.
Yes.
This table is for outbreak investigation, the steps of outbreak investigation based on Gordis epidemiology. Uh, why I show you this slide? Because today I want to talk about descriptive and analytic studies in outbreak investigation. So you should know the steps of outbreak investigation to find the suitable steps for using descriptive and analytic studies. Uh, so at first, I should introduce you the steps of outbreak investigation. Investigating of an outbreak may be deductive or inductive. Uh, Deductive means a reasoning from a previous knowledge, and inductive is a exploratory approach in philosophy. And we can have both of them, both of these approaches for outbreak investigation. For example, sometimes we have a previous knowledge, a previous information about epidemic of a disease, and we generalize this knowledge to our case. But sometimes there is no previous information, and we should inductively reason about the current ongoing outbreak. Important considerations in investigating an outbreak of infectious disease include determining that an outbreak has in fact occurred and defining the extent of the population at risk, determining the measure of spread and reservoir, and characterizing the agent. Steps commonly used are listed below, but depending on an outbreak, it's a very important note. Depending on the outbreak, the exact order may differ. Um Sometimes we should use this order, these steps in other order. Uh, I want to say you the examples later. The first step, and define the outbreak and validate the existence of an outbreak. And this step in turn falls into four categories. Uh, the first one is define the numerator or number of cases, which includes clinical features. Is the disease known? What are its serologic or cultural aspects? Are the causes partially understood? The second one, B, define the denominator. Uh, what is the population at risk of developing disease? That is, what are susceptible? These sub-steps A and B creates a fraction numerator per denominator, or means cases per population at risk. C. Determine whether the observed number of cases clearly exceeds the expected number. As I said in the previous slide, I showed you the difference between endemic and epidemic. When we say epidemic, it is the time that the uh, observed cases exceeds the expected numbers. When the observed cases exceeds the expected numbers, here we have epidemic or outbreak. And D, calculate the attack rates. Attack rate, as I will say you in the next slides, is an index for this description of epidemic. It is used for descriptive statistics, descriptive study design, attack rate. I will show you its formula in the future. Um, the second step, we define cases according to time and place, and also we look for time-place interactions. The third step, look for combinations or interactions of relevant variables. The fourth step, develop hypotheses based on the following. In this step also, descriptive study helps us for developing hypotheses for analytical studies. This step in turn falls into three categories. A, existing knowledge, if any, of the disease. B, analogy to diseases of non-etiology. And C, findings from investigation of the outbreak. And the most important, or it's better to say the most related to this topic step in this slide, which is test hypothesis, the fifth step. In this step is the step when we have worked with it, and we will talk about analytic study design. So pay attention to this step, test hypothesis, which falls into two categories. A, further analyze existing data, for example, case control studies. And B, refine hypotheses and collect additional data that may be needed. The sixth step, recommended control measures, which in turn falls into two categories: control of current outbreak, and B, prevention of future similar outbreaks. So I will tell you this point later. The seventh step, prepare a written report of the investigation and the findings. And the final step, the eighth step, communicate findings to those involved in policy development and implementation, and to the public. So, as I mentioned before, these steps may be different, may have different orders according to different outbreaks. For example, regarding I said you I will I said you I would give examples in the future. Now I am saying the examples for this. For example, step 5 and step 6. Step 5 is test hypothesis, and step 6 is a recommended control measure. Sometimes in some outbreaks, we should substitute these steps. For example, for influenza, we cannot wait for a case control study. That's the disease is spreading, and we have no time. We should recommend, we should rapidly recommend control measures and control the outbreak, and uh, we can design our studies then after the recommended control measures. Sometimes the orders are different according to the different outbreaks. So I repeat this point. Uh, Sometimes testing the hypothesis is times consuming, and we cannot wait for it. And therefore, uh, we should give our control measures recommendations, and then come back and conduct analytical studies. So these were the steps of outbreak investigation. First of all, I will uh, give you descriptive methods, and then I will sell you the analytical methods. For descriptive methods, I will give you some points. It illustrates an outbreak using 3 standard variables: time, place, and person. Descriptive methods are regarding these 3 entities: time, place, and person. I repeat again: time, place, and person. It makes it possible to set up specific hypotheses about causes and sources of infection and modes of transmission. For example, of the time, uh, we can mention epidemic curves of outbreaks. Using the epidemic curves of outbreaks is used as a descriptive method in outbreak investigation. For place, we can study spatial distribution. For example, we conduct GIS studies and any spatial distribution studies. These are descriptive methods. And sometimes we can combine time and place. We have spatiotemporal models. And spatiotemporal models may be descriptive or analytical also. And the third one, person, portraying the outbreak population. So I repeat again, the main concepts regarding descriptive methods are time, place, and person. Another method in descriptive outbreak investigation is cross-tabulation. These tables are from Gordis textbook. It is an example of epidemic uh, for persons who ate beverage and egg salad sandwiches. Using cross-tabulation, we want to find the source of epidemic, the source of outbreak. In the first table, we have two columns, ate and did not eat. And we have two rows, beverage and egg salad sandwiches. Uh, as you see, the attack rates, the attack rates in the group did not eat were low, but the attack rates in the group 8 are high. For example, for beverage, the attack rate is 67.8%, and for egg salad, the attack rate is 77.9%. So we want to differentiate between beverage and egg salad and to find which one of them are the source of this outbreak. And the next cross-tabulation is used for this aim. In the next cross table, we have two columns, ate egg salad and did not eat egg salad. And in each group, we compared drank beverage and did not drink beverage. As you see, there is no difference between the percentages for drinking or not to drink beverage. But for eating egg salad, there's a significant and meaningful and high magnitude difference between the percentages. As you see, for example, in the group drank beverage, is the attack rate is 75.6 versus 26.4. And for the raw did not drink beverage, the attack rate is 80 versus 25. So we can find the main source of this outbreak, and it is egg salad and sandwiches. Is the main source of the mentioned outbreak. I gave you this example to show the importance of using descriptive methods in outbreak investigation. It can generate hypotheses for further investigations and conducting analytical research. For example, after this cross-tabulation, we can generate this hypothesis that egg salad may be a source for an outbreak. We can conduct a case control studies. The cases are sick are non-sick persons, and the controls are people who are not sick. And then we compare the exposure proportions in these groups, which is egg salad. And as I will say you later, as I will tell you later, the, we can report the association measures as odds ratio, and find that, for example, the odds ratio of using egg salad is, for example, 4, for example. So this slide was related to descriptive methods. In continue with descriptive methods, I am introducing you some descriptive indices that are important for descriptive step of outbreak investigation. Of course, the indices are more than what mentioned in this slide, but I gave you in this slide some of the most important ones. The first one is case count. The number of cases counted, as it is self-representative. The second one is attack rate. The next one is prevalence. The next one is incidence. I will tell you the formulae. The next one is R0, or basic reproduction number. It means that an infected patient can infect how many numbers of other persons. And then the final one is case fatality rate, or CFR. The formulae. The attack rate is the number of people who got sick per total number of people exposed. This is important. Per total of people exposed to the source. This is attack rate. Prevalence is the total number of cases, whether new or existing cases, per total population. And the final one, it is incidence rate, a number of new cases in a time period per total population at risk. As you see, attack rate is a kind of incidence rate, and it deviates from incidence rate. So I gave you information regarding descriptive methods and outbreak investigation, and now I will give you analytical methods in the outbreak investigation.
If you can interrupt him and ask your question. You're all set? Okay.
Your sound is weak. I
ask them to question if they have any Would you please let us? Some
Yes,
people
yes.
have question
I wanted
before you
to
shift.
I wanted
Before you,
to give a break time about 1 or 2 minutes, and after this break time, about 1 or 2 minutes, I will
answer
respond
your question. Okay.
your questions.
Okay. Great.
Thanks.
So go on. Thank you. You can do. You can go, and after you finish your speech, we will ask our question. We are waiting for you. Please continue.
Yes. Um, I will continue the slides about 30 seconds later. Thanks.
Okay.
Thank you for your attention. I am continuing the presentation, and this slide is regarding analytical methods. And please pay
Sorry for
attention.
interruption, Dr. Yasin. Sorry for interruption because everybody goes for drinking some teas. Maybe you can start around 10 minutes later. It's okay
Yes,
for
yes.
Okay, great. Thank you. Sorry for misunderstanding. Some they think by themselves that you get them a break. So
I said about 1 or 2 minutes.
okay,
No
so it
problem.
was okay. It was a misunderstanding. Sorry.
Yes. Uh, I
I will.
wait about 10 minutes.
Is it okay?
Um,
5 or 10 minutes. You will be here. Maybe you can see the videos, the real-time videos of the participants. Is it possible for
yes,
you?
yes.
It's
I
okay.
am watching them.
Okay, great. So,
This video is being recorded. Am I correct?
Yes, Dr. Yasmin, it's recorded, the Zoom. Do you want the recorded video? I can ask them.
Uh, it is better to have access to the recorded videos for giving them in the future to Iranian
Yes.
students who are
Yeah,
interested.
sure, sure. I will ask them for share link, and I will follow it to forward it for you.
Thanks.
Great. Thank you. So the paper you share. As an anti-aging, yes. They show somewhere here that is so we cannot. I can just send it to you. That's as a template. They are exactly conditioned. I just make some there for your find out it. It's the thing in the and I just need all the safety and like all the consent. If basically and also to show if there's a for you, one other just share that it has some guidelines that you will if you need it more details, yes, I can go over this and you can see this yeah.
Dear Dr. Sana, let me start by reviewing the descriptive methods until the audience coming back.
Yes, Dr. Yassin, let me ask them to come back to their seats and we will be at your service. Everybody are here? We have all? Let me, 1 minute. So everyone now, no, they are not here.
First, I review descriptive methods until coming back.
Okay.
So descriptive methods, as I mentioned, are related to time, place, and person. These are the variables about descriptive methods. For example, for the time, we have epidemic curves of outbreak. For the place, we have a spatial distribution. And for person, we have portraying the outbreak population. Or we can have combination of them. For example, spatiotemporal models which can be both descriptive and analytical. I gave you the example of cross-tabulation as a source for generating hypotheses regarding analytical studies. I introduced you some descriptive indices. For example, case count, attack rate, prevalence, incidence, R0, and case fatality rate. Now, I will talk about analytical methods of study design and outbreak investigation. There are two main designs, including retrospective cohort studies and case control studies. We cannot have a prospective cohort study because logically and ethically, we cannot follow up the person who are exposed to a source, and therefore prospective cohort studies are not common, but sometimes it may be conducted. But usually the main designs are retrospective cohort studies and case control studies. You see two diagrams in this slide. The left one is for the design of a case control study, and the right one is for the design of a cohort study. First, for the design of a case control study. In a case control study, our approach is from cases and controls, or from the outcomes toward the exposure. I repeat again, our approach is from outcome toward exposure, from outcome toward exposure. But in cohort study, it is vice versa. Our approach is from exposure toward outcome, from exposure toward outcome in cohort studies. In case control studies, as I mentioned, I approach to the outcome. We have two groups, cases that have the disease and controls. The individuals do not have the disease. And then we investigate whether in each group persons are exposed or not exposed. But in cohort studies, as you see in the right diagram, we approach to the exposure. Therefore, we have two groups, exposed and not exposed, and we investigate and we follow up the individuals to investigate whether a disease develops or disease does not develop in each group. This is the difference between cohort and case control studies. I want to compare the features of case control and retrospective cohort studies. We compare some features, including sample size, costs, study time, a rare disease, rare exposure, multiple exposures, multiple outcomes, natural history, disease risk, recall bias, loss to follow-up, selection bias, and population not well circumscribed. I start from sample size. The first column is for case control study, and the next column is for retrospective cohort study. For sample size, in case control studies, we need smaller sample sizes. But in retrospective cohort studies, we need larger sample sizes, larger study sizes. This is the benefit of case control studies compared with cohort studies that we can conduct a case control study with a smaller sample size. Regarding costs, case control studies have less costs than retrospective cohort studies. Um, it is obvious because cohort studies are larger regarding study size. About study time, both of them can be short. About rare disease. About rare disease, case control studies are efficient, while retrospective cohort studies are inefficient. Uh, Case control studies are efficient for rare diseases, as I mentioned in the previous slide. In cohort studies, we follow up the individuals to see whether they develop or not to develop a disease. So if the disease is rare, uh, we should have a large sample size to find enough uh, sick patients, sick individuals. So it is not logistically possible. And therefore, for rare disease or rare outcome, cohort studies are inefficient, while case control studies are efficient because we can select cases even they are rare, and we compare them with controls. For rare exposure, uh, it is vice versa. Case control studies are inefficient, while retrospective cohort studies are efficient. Because we in cohort studies we categorize based on the exposure, and therefore we can select enough number of exposure positive individuals. So there is no problem for finding enough exposures. So as I summarize, for rare disease or rare outcome, case control study is better. And for rare exposure, cohort studies are better. For multiple exposures, in case control studies, we can examine multiple exposures. Also, in cohort studies, we can examine multiple exposures. But for multiple outcomes, we cannot examine. Logically, we cannot examine multiple outcomes in case control studies because we categorized the groups based on a specific outcome. And we cannot investigate the other outcomes logically as you think. But in cohort studies, the beneficial point is that we can examine multiple outcomes because we follow up the exposed and not exposed individuals, and we can see whether they develop any disease or any other outcome. So this is the beneficial point of retrospective cohort studies. For natural history, case control studies cannot ascertain, while retrospective cohort studies can ascertain. For disease risk, disease risk cannot be measured in case control studies, but in cohort studies, disease risk can be measured. For recall bias, Both of them have a potential problem for recall bias. Loss to follow-up is not an issue in a case control study because we are not following up the individuals in a case control study. But as we follow up uh, the individuals in cohort studies, loss to follow-up may be a potential problem in cohort studies. Selection bias is proposed for both case control studies and retrospective cohort studies. For both of them, we can have potentially have selection bias. And for a population not well circumscribed, it is advantageous for case control studies, while it is difficult in retrospective cohort studies. As you see in the table, case control studies had some beneficial points, and cohort studies had some other beneficial points. Therefore, we cannot say which one is better. It depends on our situation and setting. For example, when the sources of infection or sources of outbreak are known or well known, we can conduct a cohort study to follow up the exposure. But sometimes we do not know which exposure is suspected. And therefore, we can approach from the sick patients, and we should choose case control studies. About designing studies in the field. Many outbreaks are solved using descriptive information, but some require formal epidemiologic studies. That means analytical studies. And shared exposures among cases do not necessarily prove causation and demanding analytic verification. Epidemiologic studies aim to determine whether a particular exposure is associated with a disease. Such studies compare two groups, an index exposed or diseased groups and a comparison group. Index group in a cohort study are exposed groups, and in a case control study as a disease group. Proper study design strengthens causal inference and supports public health decision making. Field studies often balance scientific rigor with real-world and constraints like time and resources. The field investigator must choose designs that are feasible under emergency conditions. Analytic studies help and confirm hypotheses generated during descriptive stages of investigation. As I mentioned, we have steps of an outbreak investigation. In the first steps, we conduct descriptive studies to generate hypotheses, and in the final steps of outbreak investigation, we test the hypothesis to find the reason of the outbreak for control measures. These designs in cohort or case control allow quantification of associations between exposure and disease. The point is quantification and to find a numeric indices. The chapter of this book, a field epidemiology book, emphasizes practical methods for designing valid, efficient studies during outbreak response. About defining exposure groups. Accurate exposure definition is essential for valid estimation of exposure-disease relationship. Exposure measures should be objective, standardized, and consistently applied. Discrete exposures or binary exposures, for example, eating a specific food, as I mentioned in the example of cross-tabulation, may seem simple but require clear operational definitions. Memory lapses can bias exposure data, use records or aids like menus or vaccination cards. So we have some tricks for reducing recall bias. Quantifying exposure by dose or duration can reveal dose response patterns. Binary exposure categories, which are yes-no exposures and can obscure meaningful gradients of exposure. Composite measures may capture exposure through multiple related items or ingredients. Surrogate measures. About surrogate measures, for example, education as a proxy for socioeconomic status. They can be used, but require cautious interpretation. Regarding definition of outcomes or case definition. A case definition provides uniform criteria for classifying disease presence. Standard definitions ensure consistency and reduce outcome. Misclassification. I will tell you what is a misclassification. And criteria typically include clinical laboratory and epidemiologic elements. Restrictions on time, place, and person define outbreak boundaries. These are the points related to the case definition. When we define a case, when we introduce a case, when we label an individual as a case, we should consider these points. For example, which person at what place and at which time are known as case. And simplicity and objectivity. Objectivity. For example, specific test results or symptoms thresholds uh, improve reliability. And the definition must exclude exposure criteria to avoid a circular logic. And categories of certainty, suspected, probable, and confirmed allow flexibility. So the cases can be fall into these categories: suspected cases, probable cases, and confirmed cases. Consistent application over time and location ensures comparability of cases. So I will talk you about cohort studies. Cohort studies follow exposed and non-exposed groups to assess disease risk. They are conceptually oriented from exposure to outcome. I say again, from exposure to outcome. It is ideal when the entire population is well defined. For example, in wedding guests. It is appropriate for investigating relatively rare exposures. As I mentioned in the table in previous slides, cohort studies are better for rare exposures, while case control studies are better for rare outcomes. It is inefficient for rare diseases due to few outcome events. It can measure incidence and directly estimate risk ratios. So this is a beneficial point of cohort studies. Retrospective cohorts use existing data while prospective ones track forward. Vulnerable to loss to follow-up affecting validity. It requires careful exposure classification to avoid misclassification bias. So we should pay attention to correctly classify the exposed and not exposed groups. When we consider an exposed individual as a not exposed individual or vice versa, we have misclassification bias. Misclassification can be proposed also for outcome. I will tell you about misclassification. External comparison groups can introduce healthy worker effect. A healthy worker effect is a kind of selection bias that it is present in observational studies like case control and cohort studies. So you can search for healthy worker effect or healthy worker bias. They are good information. There are good information in Wikipedia about healthy worker effect or healthy worker bias. Well suited for assessing multiple outcomes from one exposure. As I mentioned, it is a beneficial point of cohort studies that you can investigate multiple outcomes from one exposure. And conceptually, and simpler, but often more resource intensive than case control designs. Uh, from this slide, I will talk you about case control studies. The first subcategory of my presentation regarding case control studies are selection of cases. And case control studies begin by identifying persons with the disease of interest. Cases must meet the previously established case definition exactly. The source population for cases should correspond the total population from which controls will arise. It is a very, very, very important note. Uh, of course, in outbreak investigation, the cases are more clear than in other situations. And therefore, we have no problem in outbreak investigations. And cases can be found through surveillance, hospitals, and outbreak line listings. Therefore, we can select non-cases from these sources, from surveillance, from hospitals, and from outbreak line lists. Inclusion of all eligible cases reduces selection bias. For example, you have an outbreak investigation and totally, for example, you have 80 cases. If you choose all these 80 cases as cases of your case control study, you reduce selection bias. Early identification ensures exposure information remains accurate. When possible, newly diagnosed or incident cases are preferable to prevalent ones. It is an important note because when you approach to incident cases, new cases, you are sure, you are ensured that the cases are real and temporarily they occurred after the exposure. Clear diagnostic criteria ensure comparability across sites. Case ascertainment should be complete and not convenience-based. Excluding secondary or unrelated cases maintains analytic validity. About selection of controls. Selection of controls is very important in case control studies. Controls represent the population from which cases emerged but without the disease. Their exposure experience should reflect that of the source population. Cases and controls should have the same source, same arising population. And controls can be selected from households, neighborhoods, hospitals, or community samples. Random or systematic sampling minimizes selection bias. And another point is that the ratio of controls to cases is 1 to 1 up to 4 to 1, which increases the statistical power of studies. Overly similar or overmatched controls can mask true associations. So we should prevent overmatching uh, the cases and controls. Friend or a neighbor controls are practical but may introduce bias. Matching and confounders can help control distortion in analysis. So it is an extra point I'm talking to you. Matching can be based on confounders, based on mediators, or based on colliders, but it is not suitable. It is wrong when you match based on a collider. It is a wrong act. And matching based on mediators results in overmatching. And the best type of matching, or the only suitable, is better to say the only suitable type of matching is matching based on confounders, based on the variables that have the role of confounding. And so when you match the demographic information in two groups, consider that the variables should be confounder. The choice of control group depends on feasibility and comparability. High participation rates among controls are essential for validity. Most case and control studies use case-to-control ratio of either 1 to 1 or 2 to 1 or 3 to 1. About matching, I gave you some further information. Matching equates cases and controls on potential confounding factors. Of course, there's an extra point that a more important reason for matching is to increase the statistical power, but it is not mentioned in the use chapter. It can be done individually, named as pair matching or by frequency. Pair matching assigns one or more controls with identical key traits to each case. Frequency matching ensures similar overall distributions of confounders. Matching simplifies control of confounding during design, but complicates analysis. Overmatching reduces exposure contrast and statistical efficacy. Matching should focus on strong confounders like age or sex. Analytical methods, for example, in conditional logistic regression, must account for matched design. Matching on variables affected by exposure reduces bias. Field investigators should weigh logistical convenience against analytic complexity. Regarding analysis and interpretation, the main measure of association in case control studies is odds ratio, or OR. I will introduce you OR in the next slides. I will tell you what is OR. Uh, OR approximates relative risk when the disease is rare. For example, when the prevalence of the disease is less than 10%. 2x2 contingency tables are used to compute exposure odds among cases and controls. You compute exposure odds among cases and divide it per the odds among controls, and you reach an odds ratio. Stratified analysis helps control confounding and identifying effect modification. Matching and necessities necessitates matched pair or conditional analysis. I want to talk to you 2 points. The first one is that the first bullet, the main measure of association in case control studies is the odds ratio. Odds ratio is a type of measuring association, is a type of association measure. Sometimes it is called effect measure. But philosophically, there's a difference between association measure and effect measure. Association measure it shows a magnitude of association of a statistical association. But this statistical association may be confounded by confounders, or maybe distorted by some bias. If we have no confounding and no bias, this association is effect, is causal, and therefore we can use the term effect size instead of strength of association. And the other point is for the last but one bullet, regarding stratified analysis for identifying effect modification. Effect modification is a term used for interaction, to find interaction, to show whether an effect is different in different strata of a third variable. Bias from misclassification or recall can distort effect estimates. And confidence intervals quantify precision of the odds ratio. Small samples yield wide intervals and reduced statistical power. Interpretation requires caution regarding temporality and causation. Combining analytic results with descriptive findings strengthens outbreak conclusions. You see a 2x2 contingency table, which have columns for whether event occurred, yes column and no column, and we have 2 rows, exposed and not exposed, and the cells are named A, B, C, D. The relative risk is the risk of an event in exposed group per the risk of an event in the not exposed group. As you see the formula, it is A per A plus B divided by C per C plus D. But odds ratio, in odds ratio, you deviate two odds. You compare two odds, not two probabilities. When you say A per A plus B, it is a probability. But when you say A plus A per B, it is an odds. And when you compare two odds, it is named odds ratio. And the formula is A per B divided by C per D equals to AD per CB. I want to talk about some potential pitfalls in designing and conduct of epidemiologic studies. Please pay attention to these points. The first one is selection bias, which is a potential pitfall in designing and conducting epidemiologic studies. Selection bias arises from systematic differences in how study groups are chosen. It leads to a distorted estimate of the exposure-disease relationship. It occurs when cases or controls are not truly representative of their source population, including asymptomatic infected persons as controls can dilute through associations because it's a kind of misclassification in outcome because you use some suspected cases as you consider some suspected cases as controls, and therefore the association measure comes toward null. Sorry, I will come back 1 minute later. بله سلام مرسی ممنون بله 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 راستش من الان وسط کلاسی هستم میخوام خودم حضوری خدمتتون
Efendim چطوره؟
ساعت 12 حضوری بیام خدمتتون خوبه؟ باشه 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 من خودم And sorry, I had an important phone, an important calling from university, and I should respond. About selection bias. It occurs when cases and controls. I was talking about using asymptomatic infected persons as controls. As I said, it is a kind of misclassification. It is a kind of misclassification when you consider a suspected case, an asymptomatic case as control. It dilutes the association. It shifts your odds ratio or your risk ratio toward null. toward one. Over broad case definition can introduce non-case biasing results toward the null also. Diagnostic bias occurs when knowledge of exposure influences disease and classification. Volunteer bias can occur if participation depends on exposure or health status. Loss to follow-up in cohorts and can create unequal comparison groups. Random or blinded selection methods help minimize this bias. Awareness of selection bias should guide both design and interpretation of studies. Now I will talk about information bias as a potential pitfall in designing and conducting epidemiologic studies. Information bias results from systematic errors in measuring exposure and outcome. Misclassification of exposure or disease can be differential or non-differential. I will show you what is the difference between differential and a non-differential misclassification. Recall bias is common in case control studies when cases remember exposures differently. Interviewer bias occurs when questioning differs between groups. Surveillance bias can arise when certain groups are more intensively monitored. So we have many potential sources of information bias. Using standardized questionnaires minimize measurement variations and training interviewers and blinding them to hypothesis reduces bias. Objective records, for example, lab data, are preferable to self-reports when available. Consistency in data collection tools across sites ensures comparability. And careful pre-testing and pilot studies can reveal potential information biases. This is a diagram showing misclassification. We have misclassification of exposure and misclassification of outcome, and which of them can be differential or non-differential. What is misclassification of exposure? The first row, the above row. Misclassification of exposure is the time when you consider as a exposed group as a not consider exposed group as a not exposed group, or vice versa. When you consider a not exposed group as a exposed group. When it is differential, the left figure is differential misclassification because in one group the magnitude of misclassification is more, and therefore it affects your association measure. About misclassification of outcome. It occurs when you consider a case as a control or a disease case as a not case, or vice versa. When it is differential, it is differential when in one group you have more magnitude of this misclassification than the other group. Therefore, it affects your association measure. It affects your odds ratio or your relative risk. Another pitfall is confounding. And confounding occurs when an extraneous variable distorts the exposure disease link. A confounder is related to both exposure and the disease, but not on the causal pathway. Uncontrolled confounding can produce false associations or mask true ones. Common confounders include age, sex, smoking, and socioeconomic status. Control methods include restriction, matching, stratified analysis, and regression modeling. Some of controlling methods are for study design, for example, restriction and matching, and some others are at the level of analysis. For example, stratified analysis and regression modeling. This is the diagram showing confounding in the relationship of exposure and outcome. It is wrongly written in the figure. The right one and the right box should be outcome. It is wrongly written exposure. Please correct it. For example, in the association of coffee and cancer, smoking is a confounder because smoking is a common cause for both coffee and cancer. Smoking is a non reason for cancer, and smoking also is associated with coffee use. Another pitfall in the design is a small sample size. Small sample size limits statistical power to detect meaningful associations. It increases random error and yields wide confidence intervals. Statistically, non-significant findings may still reflect real associations. Small studies are vulnerable to unstable estimates due to few events. Power depends on effect size, exposure prevalence, and group ratio. In outbreak investigation, sample size often constrained by available cases. So it is a limitation of calculation of sample size in case control studies. Underpowered studies may fail to detect important public health risks. Larger studies enhance precision but may not be feasible in emergencies. Pre-study power calculation can guide adequate enrollment targets. Interpretation of small sample studies should emphasize effect magnitude and biological plausibility over p-values. As p-value is affected by statistical power. For example, when you have an overpowered study, your p-values are less and more meaningful, and vice versa. More important than p-value is biological plausibility, and you should emphasize in small sample studies. You should emphasize effect magnitude or biological plausibility. So I summarize my presentation at the final step. Cohort and case control studies are the two primary analytic tools in field epidemiology for testing hypotheses generated during descriptive investigation. So I repeat again, descriptive investigations generate hypotheses for analytic investigation. Cohort studies, moving conceptually from exposure to disease, suit well-defined closed populations, for example, wedding guests or workplace groups. Case control studies oriented from disease to exposure are preferred when the study population is less defined or cases are rare. Designing a valid analytic study requires careful choices about comparison groups, control ratios, matching, and bias prevention. Successful field study design balances methodological rigor with practical constraints, ensuring credible evidence for public health action. Briefly, I tell you that when an outbreak occurs, we have steps of outbreak investigation. In the first steps of outbreak investigation, we descriptively analyze the information and the data, and we generate hypotheses for analytical studies. And in analytical studies, we have cohort and case control studies to test our hypothesis. Thank you for your attention. I'm waiting for any question. Thanks. Many thanks for your attention. Thank you.
Thank you, Dr. Ahmadi.
Excuse me.
Can you hear us? It's not working. Mute तो नहीं है ना?
I'm waiting for any question.
There is one question. Hasifa, please come. Okay, you also have question.
Okay.
Mic, let the mic work, then ask. Okay.
Okay, thank you, Doctor, for a comprehensive and a very well formative presentation. Is it audible? Can you hear me?
Yes,
Sorry.
yes.
Okay. Thank you for a comprehensive and a well-structured presentation. Just have one question, because we are dealing with emergency outbreak preparation in case of pandemic as well as endemic. My question goes to, like, if the case is very urgent, so are there any ethical consideration during emergency outbreak, like a normal state as well? Thank you very much.
Yes. In emergency conditions, we should consider different thresholds for defining an outbreak. For example, in emergent conditions, and we should not wait for a rising and the curve, the epidemic curve, for large amounts. We should consider lower thresholds to detect an outbreak. It depends on what threshold we choose for deviation from the expected numbers.
Thank you. Okay, sure. Continue. No, go on.
Okay, so thank you so much, Doctor, for that very beautiful presentation. And I actually have not one question, it's actually a series of questions that may require you to kind of like help to have an overview of the whole presentation. Again, as I ask the questions, is that okay with you?
Yes, please say your question.
All right, so the first question, if you go back to the first page where we had, I think it was the indices, descriptive indices. You remember that slide?
Yes.
Yeah. So R0, I didn't get exactly what R0 means or when it's used.
R0 shows that consider an infected patient. So this infected patient can infect some other patients as its disease is contagious. Okay? He or she can infect other patients. R0 is the number of number of individuals that an infected patients can affect. For example, when R0 is 5, it means that an infected patients can transfer the disease to 5 other persons.
Does it have
Okay.
an element of time? And is there a formula for it?
And there is no formula. It is a concept.
Oh, okay. So what would be the general relevance of that concept when it comes to the topic or outbreak investigation? How would we use that information?
When R0 is equals 1, it means that outbreak is stopped. When R0 is less than 1, it means that the outbreak is stopping. is going to be stopped. And when R0 is more than 1, it means that the outbreak is forming, and we have a outbreak in future. Of course, it is Rn. We can primary basic reproduction number and secondary reproduction number. Do not confuse. Consider the threshold number 1. When R0 is more than 1, the outbreak is forming. The outbreak is developing. When R0 is more than 1, it means that one infected patient can transfer the disease to more than one other. Okay?
All right, that makes sense. Thank you so much. So the next question is going to be on the slide that what you were describing. I think it was the attack rate, and it had a series, it had tables that were blue in color.
This slide?
Yes, that slide. So I just need your clarity. As you were explaining, you were hinting on the causation for the sickness, in this case, to be caused by people who, by eating egg salad or something like that. So I want you to kind of like explain to us what could explain the cases that are seen in people who did not eat the egg salads. Because I would expect, if we are saying that the egg salad caused whatever we are seeing, I would expect the percentage, the other side, to be like 0 or anything closer to 0, so we can speak with certainty.
Yes, I understood your question. You say that what in why in the column did not eat, the attack rates are not 0 or close to 0. It is also a question for me. This example is from Gordis epidemiology book, and you can refer to the source of this example and find why the attack rate is not 0 or close to 0. Please refer to the resource, to the main book, Gordis epidemiology, and in chapter 2, and find this example. Of course, this example is from another source. I mean that Gordis also used another source, as he mentioned a reference for 1974. Is also a question for me. Please look at the main source.
All right. Thank you for that. We'll be able to do that. Then the third question. If you go to the page where you were describing matching and kind of like review for us that part of it.
Matching?
Yeah. Yes. Yeah, so like how the exam, like exactly what you meant by matching and how you would execute the matching in case control studies. And if you have like a matching, an example of how this can be applied of an actual disease or an actual situation where matching has occurred, I think it will give us very good understanding of the process.
Yes, let me give you an example. For example, you have two groups of cases and controls. For example, the first case is a 30-year-old woman. So you choose a 30-year-old woman also for a control group to match these two individuals. And the second case is a 40-year-old man. A 40-year-old man, and you find also a 40-year-old man for a control group to compare these individuals between two groups. These are matching. You matched cases and controls based on age, based on sex, based on education level to create comparable groups, to create similar groups, and to control the demographic variables. Okay.
Okay, and the concept of confounding, how does it come into this mix?
So it controls confounding because the third variables, variables with third roles are distributed similarly in the two groups. They are distributed similarly in the two groups, and therefore you can compare the groups without confounding effect of these third variables. For example, when you match ages, you matched ages. For example, the mean of age in cases is 40 years old, and the mean age in controls are also 40 years old. Therefore, age cannot affect your result, cannot affect the relationship between exposure and the outcome. Okay?
Okay. So if you were doing like a study and you find the confounders are not equally distributed, or they are probably skewed in one group other than the others, so what would you do statistically?
For controlling confounders in general, we have two approaches. Controlling at a design level, study design level, and controlling at analysis level. Controlling at design level is related to study design, is related to the time when you when the study is not started. It is controlling confounders at study design. And the examples are restriction and matching and randomization. Restriction is having inclusion and exclusion, restricted inclusion and exclusion criteria for individual selection. For example, you restrict to choose who persons. And matching was which I tell you, and the other one is randomization. You randomize the groups, which is used in clinical trials. These three methods are used at design level. And also we have three methods at analysis level, as you asked. The three methods at analysis level are stratification, regression modeling, and instrumental variable analysis. Stratification is that you conduct a stratified analysis. For example, you conduct the analysis of an exposure and outcome one time in men and one time in women. It is a stratified analysis. For example, one time in individuals less than 40 years old, and one time in individuals more than 40 years old. It is a stratified analysis which can control confounding effect. The other one is regression modeling. In regression modeling, you have multivariable modeling or multiple modeling that you import more than one variable to the model when using the software for analysis. You import, other than the exposure, you import age, for example, and sex to the model, and you predict the outcome with the exposure, age, and sex. Therefore, it is a multivariable model. And each association, the association measure of each of them are attributable to the related variable. For example, when you added age and sex to the model, you controlled the association of exposure and outcome for the effect of the confounding effect of age and sex. You can search multivariable modeling or multiple modeling, and please remember to search these terms. And the third one is instrumental variable analysis, which is a very complex concept and is not suitable for this session. You can search for instrumental variable analysis, and if you have any more question, please search what I said. And if you have any further question, you can contact me via my email. Okay?
Okay. Thank you so much.
You can capture, take a photo from this slide showing my email by your cell phones.
Actually, Dr. Ahmadi, if you let me, they asked me to share the slides. If you let me, I will share the whole lecture of yours with them, and they will have the Zoom link as well in near future. Okay. Thank you.
I will share my slides through Dr. Sana, and she will give you my slides.
I have already have your slides. You know, she sent me yesterday. I have. If you let me, I will share with you.
Okay. There's no problem.
Okay, thank you. Thank you for your time and your interesting lecture. Okay, goodbye.
Goodbye, everyone.